So we are there, 150 almost. Today we are going to do a virtual experiment of finding the heat of formation of ethanol, ethyl alcohol. So we talked about heat of formation. Now we're going to find the heat of formation by doing an experiment. So when we do that, we'll collect some data and then we'll have to do calculations. So we are once again going to practice. And as it was pointed out by somebody, this particular units have a lot of information that is new and a lot of different phrases whose meaning you need to understand. So it requires a lot of practicing. And the experiment is also designed to give you that practice. So we started the experiment with practicing this thing. For example, we first did the experiment about the specific heat capacity of aluminum and lead. And the specific heat capacity, we understand the word specific heat capacity. Specific means a particular object, and a particular object means an object that is homogeneous, not heterogeneous. So those pieces of metal, aluminum and lead, they were specific. So they have a specific heat capacity, their capacity to hold on to heat, so to speak, and not let it go. That's what we are talking about, heat capacity. Specific, their capacity is specific, but a calorimeter is not made up of one thing. It is a heterogeneous substance. So the calorimeter cannot have specific heat capacity. It just has heat capacity. When you have specific heat capacity, grams are part of it because it has to do with how much you have. When you have heat capacity only, you cannot have grams because whose gram are you talking about? The calorimeter could be made up of many things. So whose gram are you going to talk about? You cannot talk about grams of calorimeter because the different things that the calorimeter is made up of has different heat capacity. So you cannot talk about grams. Different specific heat capacity. If the calorimeter is made up of steel and it is made up of glass, it may have glass inside, glass bottle inside. It may be outside. It may have aluminum. It may have some air in it. It may have some other stuff in it. So you cannot say this is a specific thing. It is a heterogeneous thing. That's why we cannot talk about specific heat capacity when we talk about heterogeneous things and talk about calorimeters. So you only talk about heat capacity. So what is the difference between specific heat capacity and heat capacity? And we say the units, look at the units. Of course, grams are not going to be part of the specific heat capacity. It's going to have grams in it. C, small c, equals grams multiplied by, Q equals gram multiplied by, not small c. Small c equals, we're gonna say Q equals gram multiplied by small c multiplied by by delta T. And the other one, now we say Q equals big C multiplied by delta T. There is no gram. That's the difference. And delta T is, we are not going to add 273 after calculating delta T, because delta T is Kelvin and Celsius, it's the same thing. So in the last experiment, in this experiment, last part here, we had, we went from 20 degrees Celsius, 20 degrees Celsius to 25.6 degrees Celsius. Then the delta T is just going to be 5. So actually 25 minus 20, because final minus initial. So that's going to be plus 5.6 degrees Celsius. That's what we decided. Minus 20 and plus 25. 5.6 degrees Celsius. And it's the same thing as 5.6 Kelvin. No, we are not going to add 273 to 5.6 when it concerns delta T. And I have shown you many times why that is the case, because you are adding 270. If you want to add, you have to add 273 over here, 273, and then you add 273 over here. Because you have to convert this into Kelvin, and you convert this into Kelvin. And when you do that, of course, this is going to be negative here, and this is, this is going to work out to be 5.6 K. Okay. And we talked about energy. And we say, we are not concerned with absolute energy, how much energy a system has. We are concerned with changing energy. And changing energy because of a chemical reaction, that's what we are concerned about. We are not concerned about anything else. Or a physical process that's similar to a chemical reaction, that is, changing the state of water, for example, that kind of thing. So delta E, that's what we are talking about, this delta E. And delta E equals Q plus W. And Q is the heat, and W is the work part. The energy change that happens of anything, it has to do with only two things: change in the heat and change in the work. Like, you think about the car. That's the easiest thing to think about. A car, when you turn it on, it does work by it changes energy by two things: by giving out heat into the surrounding and by doing the work. So those are the two ways energy changes. There are many different kinds of energies, but that doesn't make any difference. These are the only two ways we can do the change. So delta E equals Q plus W. And this W has to do with P delta V work. In chemistry, we are only concerned with this kind of work. We're not talking about any other kind of work. P is constant pressure, and so change in volume is what we are talking about. Therefore, QE equals Q minus P delta V. Instead of W for work, we're going to write negative P delta V here. And then we are going to change this, do this equation, and say, we're going to say this Q here is at constant pressure. We're going to call it QP. And we're going to rearrange the equation. QP equals delta E plus P delta V. Just P delta V, sorry. Just doing that. And since this is made up of state function, this is also a state function. And we are very happy, because then we have to just add and subtract. So if this is a state function, then it requires a different name and a different symbol. We have the name enthalpy for heat of reaction, and we have symbol H. And of course, we are talking about heat of reaction, so we write down delta H reaction. This reaction can be different type of reactions, as we know. It could be neutralization. It could be combustion. It could be gas formation. So we can write that down. Instead of reaction, we can write down the type of reaction it is, and that's fine. It could also be heat of formation reaction. What is a formation reaction? A formation reaction we have defined as forming 1 mole of a compound from its constituent elements in the standard state, forming 1 mole of a compound. So we write an equation that has only 1 mole of a compound. And in order to do that, if we have to take fractions for coefficient, we will use fractions for coefficient. So that's where the heat of formation is coming from. Now, delta H reaction is a state function. So in order to find delta H reaction, we say final state minus initial state. That's how we do calculation for state functions. So we say final in chemical reaction is the product, and initial in the chemical reaction is the reactant. So final of the product minus final of the reactant. What final of the product? Final of the heat of formation of the product minus final of the heat of formation of the reactant. And that's how we can calculate delta H. So here we have delta H. Delta H equals sum of the heat of formations of product, prod, minus sum of heat of formation of reactant. That's where the equation comes from. Very simple equation. Once you understand it, there is not much to it. Where do we find this heat of formation? Either we're gonna do an experiment ourselves and find it, or we are given in the table of heat of formation. So that's all there is to it. So this is, I already went through one more time what involves in this particular units to improve your understanding. Okay, now let's see. Here we go. Just want to do a couple of more problems before we jump into the the lab. We finished this. The heat released by reacting 100 milliliter 1 molar HCl with 100 milliliter 0.5 molar barium hydroxide at 25 degrees Celsius is this much. Calculate heat of neutralization. Because this reaction is a neutralization reaction, we write down neutralization of hydrochloric acid plus barium hydroxide. There is no limiting reagent because we have exactly the same amount moles of hydrochloric acid that is needed to react with same number of moles of barium hydroxide. Double the moles of hydrochloric acid because we have 2 hydrochloric acid here. You can see that 0.1 molar hydrochloric acid we have here, and we have 0.05 molar barium hydroxide. And that is correct because we have 2 to 1 relationship in the 2 mole to 1 mole relationship in the reaction equation. So we want to find out delta H. The heat released by the reaction is already given to us. This is the heat released by this reaction. and it is heat released by how many moles of HCl and how many moles of barium hydroxide? It would be the same mole of HCl and same mole of barium hydroxide because there is no limiting reagent. So we can do either one of these two to find the moles of barium hydroxide or hydrochloric acid. And then that would equal this many kilojoules of heat. And then we can find delta H. Then we have 2 moles of HCl in here and 1 mole of barium hydroxide. That's how we can do that. So let's find out how many mole of HCl we have here. Very simple. Everybody see that is 0.1 mole of HCl. We can do the calculation. .100 liter acid. That's 100 milliliter of acid. 1 molar, so we're gonna multiply that with 1 mole A divided by 1 liter A. Put it in the parentheses so you guys can see it better. So now we have 0.100 mole of acid. And that is responsible for giving us this much heat, equals 5.9 kilojoules. How many moles of HCl do we have here? 2 moles in the equation. So we want to know, this is our conversion factor. Our given quantity is 2 mole of HCl. That's given from here. So we write down 2 mole of HCl, 2 mole of acid, multiply that with the conversion factor. See, this is why I was telling you that knowing dimensional analysis makes life easier in this chemistry. Because we're gonna refer to that. Yes, okay, this is our conversion factor, and everybody now understand what a conversion factor is and what it can do. We are converting one unit to another unit. That's what we are doing. We are converting from units of we are converting either from one unit to another unit, or we are converting from keeping the unit same, but converting from one substance to another substance. So we are going to multiply this conversion factor that we just made up. Nobody tells you that there is a conversion factor. This is a conversion factor, of course. I'm going to write it down over here now. 0.1 mole A, 5.9 kilojoule. It's going to be negative 118 kilojoules. Negative 5.9 here. Remember that? That's why negative 5.9 here. Negative 110 kilojoules. 118. And I have only 2 sig fig over here, so I should not be, how many sig fig I have? Only 2 sig fig here, so I should be writing it as not at that number, but I should be writing 1.2 multiplied by 10 raised to 2 kilojoules. That's how I should be writing. So that's the heat of reaction, neutralization reaction, heat of neutralization. And this is the Q that was found by experimentation. So this is the relationship between Q and heat of reaction. If you would have used these numbers for the base, and did the calculation, you would have the same answer, because both of them are equivalent to each other. There is no limiting reagent, that's why. Write the equation for showing formation of 2 moles of ammonia gas from its constituent elements. We did that. Write equations forming only 1 mole of ammonia gas from its constituent elements. Well, that's easy to do. Everybody can write that down. We just from 1 mole, you are going to use fractions for coefficient. And I already wrote this down actually, and it is written down. It has been written down before. Now we have this reaction here, 1 mole, and that's gonna be written down is like this, 1/2 N2 plus 3/2 H2, giving you 1 mole of NH3. That is the point, NH3. That's the HEAT formation is negative 92 kilojoules. So we'll write that down over here, negative 92 kilojoules. This is what example 13b is. Now, example 14, you see that this reaction has been reversed. The reactant became the product and product became the reactant. So what happens to the heat of formation? The sign is changed. So now heat of formation, the number is going to be the same, but the sign is 92 plus 92 kilojoules. That's what happens to the heat of formation. If we multiply this particular equation by 4, then we multiply heat of formation by 4 to find the heat of reaction of this reaction. I mean, we multiply 92 by 4. So 92 by 4, that's going to be 8 and 36, 368 kilojoules. I want only 2 sig fig. I can manage that by saying 303.7 multiplied by 10 to the 2 kilojoules. Okay. Write the heat of reaction of 2N2 now. For what happened over here? Now we are going from here and we multiply this by 4. So it's going to be same number, but it's going to be a negative sign because now you can see why that is a negative sign. Negative 3.7 multiplied by 10 raised to 2 kilojoules. So it's a very simple thing. If you multiply the equation by 2, you multiply the heat associated with that equation by 2. If you divide it by 2, you divide it by 2. If you change the equation, if you flip the equation, what the word? Flip. If you write the equation backwards, then you change the sign. This is how you deal with the heats, the enthalpies. Heat of formation depends upon temperature. We talked about that and other stuff too. But the temperature depends of heat of formation is minuscule. So most of the time we ignore it. Now, going over it slowly and again, that's the idea. And oof, we are not gonna go too far now. Let's see. Unless otherwise noted, heat of formation is used for temperature other this is supposed to be for 25 degrees Celsius, but we also use it for other temperature unless I tell you something different. So we just use it loosely. Heat of formation depends upon the state of the product. So you must write the state of the product. The heat of formation of NH3 gas is going to be this here. -46. So that's negative 46 kilojoules. That's the heat of formation of, oops, they don't want to do that. I want to do this. Negative 46 kilojoules. But heat of formation of ammonia is not going to be the same. Everybody right now is going to Google and find the heat of formation of ammonia. Or ask Siri or Alexa, what is the heat of formation of ammonia? See what happens. What is the heat of formation of ammonia?
The molar heat of formation of ammonia is minus 45.9 kilojoules
Aha.
per gas.
It says minus 45.9, that's 46, but I did not say ammonia. It says ammonia gas. I want an ammonia liquid. So I have to tell ammonia liquid now. I don't know if it will give me that or not, but ammonia gas, we got it. What is the heat of formation of ammonia liquid?
If you like, I can search the web for. I guess we got it.
Oh, we got it. What is it? Nah, didn't get it. Okay, let's get out of there. Anybody found it? Heat of formation of ammonia liquid? Ethan Shaw? Anu Didaise, America, Michael? Anybody? Heat of formation of ammonia liquid? What is the heat of formation of ammonia liquid?
I found this on the web.
Yeah.
Negative 46 Kelvin joules.
Ammonia liquid, not ammonia gas. So we got the ammonia gas. That's negative 46 kilojoules. That's correct. But ammonia liquid will be different.
That's what I found online too. Let me.
For liquid?
I'm trying to find it for liquid. I can't find the answer yet.
Negative 30.
That make more sense.
It says while being transported and stored in specialized steel containers, liquid ammonia is kept at negative 30.
Yes. Okay.
That's hard.
Oh, for water, for liquid water is going to be 243, negative 243 kilojoules. And for gaseous water, H2O gas is going to be negative 282 kilojoules. So there is the difference there. And you just need to know that, you need to understand that we have to deal with the states when we are talking about heat of formation. That's all. You don't need to know. Of course, these numbers don't need to be known. All right. We also know that if it is a heat of formation of graphite, is going to be 0 because all elements, heat of formation is 0 because you don't have to form them. So that's very clear. But heat of formation of diamond is not 0 because you have to form the diamond. It's like, I don't remember, 2.3 kilojoules or something like that. You can find that out yourself. Let's see if that my Siri would answer that question or not. I don't know. What is the heat of formation of diamond?
I found this on the web.
Diamond Wikipedia. Diamond is a solid substance. Diamond, what is it?
I'm sorry. I can't complete your request.
Okay, sorry. Yeah. What is the heat of formation of diamond?
Here's what I found.
Not found. Okay, anyway, you guys, you can find it and it's close to this one. Is it negative or positive? I forgot. That part I forgot. It's about 2.3 kilojoules. But what the point is that it is different. That's what the point. So we have to write down Heat of formation of graphite, we have to write that down when we are talking about heat of formation of carbon. We cannot just say carbon. We have to say carbon. We have to say graphite. Okay. Write the chemical equation whose delta H equals heat of formation of water. Well, that's what we did right now. So chemical equation whose delta H reaction equals heat of formation of water or gas. And that's what I did right now here. So I'm gonna write the chemical equation, which is a simple thing to do. We are forming H2O gas from its constituent elements. So we're gonna say H2 gas. We have to write the state of this thing plus 1/2 O2 gas. Because heat of formation is about forming 1 mole of a substance from its constituent elements, O2 gas, at 25 degrees Celsius. And at 25 degrees Celsius, we don't form gas, we form liquid water. So we have to understand that, okay, that's all right. We understand it. So H2O gas. And the other equation is going to be H2O gas plus 1/2 O2 gas equals H2O liquid. And then the respective heat of formations are going to be, for H2O gas is going to be 282. You don't have to know that, of course, because it will be given to you either in the problem or you find it by looking up the table. And this is for the liquid, for the water liquid. Okay. Calculate the heat of reaction for the explosion of 4 moles of nitroglycerin according to the following equation. Heat of reaction, calculate the heat of reaction. Heat of reaction is a state function. So when you are calculating heat of reaction, you are saying final state minus initial state. And final state is the heat of formation of all the products. That's the final state. Initial state is the heat of formation of all the reactant. That's the initial state. So final state minus initial state, these are all given to you. So you just write them down, numbers, and then you find whatever you are looking for. So here we have reaction for explosion of 4 moles of nitroglycerin. 4 moles of nitroglycerin. 1 mole of nitroglycerin is this many kilojoules. And 4 moles of nitroglycerin is going to be 4 times that. And this is that. That is for 12 mole of carbon dioxide would be 12 times this. So we're going to write down the equation first of all. And the equation is write down is heat of reaction, delta H superscript 0, 25 degrees Celsius. That's what we presume that it happens all the time, which is not true for nitroglycerin, but we're going to pretend that that's okay. First of all, we write down sum of all the heat of formation of reactants, product minus reactant. Product is the final state and reactant is the initial state. So that's why we write the equation this way. Heat of formation of reactant. And then we're gonna plug it in. Product, these are the products. So 12 moles of carbon, 12 moles of this, so 12 multiplied by this. 12 multiplied by negative 393.5 kilojoules. Plus 10 H2O is going to be this one. So plus, just multiply by 10. So 2,418. 18 kilojoules plus negative, of course, there's negative. So plus negative. So this is negative here. This is negative here. And then we have 6 and 2. What is the heat of formation of nitrogen? Anybody? Quick, quick, quick. Nowhere to look. It's an element. It's in normal state at 25 degrees Celsius. Do we have to make an element by doing a chemical reaction? No. Therefore, what is the heat of formation?
0.
0, 0, 0. So these two are easy. Nitrogen and oxygen, both is going to be 0 plus 0 plus 0 minus 4 moles of this. Heat of formation of nitroglycerin is this one. So this much multiplied by 4 minus 4 multiplied by negative. I'm going to put it in the parentheses like that so I don't get confused by signs. 365. Wow, 365 for 365 days. Okay, kilojoules. So it's a simple calculation. Just add them up and we get the answer. This is the answer. It's a very big number, but that's why nitroglycerin is used for what it is used for explosion.
Professor, can you type that bottom
Sorry?
line again?
Sorry,
Can
what?
you type that bottom line?
I can read it for you. That would be easier. 12 multiplied by 393.5 kilojoules minus, this is negative 393.5 minus 2,418 kilojoules. That's for 10 moles of water plus 0 minus this whole thing is in parentheses minus 4 multiplied by negative 365.5 kilojoules. And the answer will be this one as you add it all up. So it is the same way you will do this problem. I'm going to leave that to you guys. We're going to change course now, going to do the lab. And heat of formation is what we are talking about in the lab. So let's go for it. Let's go for that. We are talking about heat of formation ethanol. This is the experiment. Heat of formation. Now, you have some idea of what a heat of formation is and what it is used for. That was the point of going through all these things. Now we do the experiment and we do some calculations. So you have a better idea again. Okay, what do I want here? I want Beyond Labs portal. What happened to Beyond Lab portal? Okay, login, chemistry, open, thermodynamics, 3.8. What happened? Oh, there we go. Thermodynamics, heat of formation ethanol. Okay. What do we have here? We have a temperature thing going. We have energy units, which are not needed for us because I'm not going to give you anything else except joules. If I give you calories, I'll give you the conversion factor. We don't care about BTU. Okay. What do we have here? Here we have a cup. It's a very, very small cup, but that's what it is, a cup. And the cup has ethanol in it. Ethanol is C2H5OH. C2H5OH. Ethanol is an alcohol. And that's why in organic chemistry you write OH. This is not an ionic substance. This is a covalent compound. It starts with C. That makes it sure that it is not an ionic compound. It's a covalent compound. Whether you have OH at the end or not doesn't make any difference. That OH is not an ion. Alcohol formula is C2H5OH. All right. That's what we have here. Now, this alcohol is in the cup and it has already been tiered. And I see that the weight of the alcohol is in the cup. Everybody's writing this down. Weight of alcohol. Now, how are you going to write it down? Let's see. Just make a little bit of a table. Later, I'll show you more. Right now, just make the table. Weight of alcohol, weight. That's that. 7847 or 46, whatever. Doesn't make any difference. 0.7847 grams of alcohol. Alcohol is a liquid and it has been, gram has been measured. Now, we are not going to use this. We are talking about a liquid. We're going to use a lab book. You can open it up if you want to. Screw cap. Screw cap is for this bomb calorimeter. This is a bomb calorimeter. And what does that mean? Screw cap, we understand. You'll screw it on top of it and it's closed. It will be as much an isolated system as possible. That's the point. Okay. What is a bomb calorimeter? Bomb. A calorimeter is like a thermos. A bomb calorimeter is like a very strongly made thermos, so it's not going to break down when we have a bomb going on inside it. That's the point. So we're going to combust something. We're going to burn something inside. And when this is going to be burned inside, it's going to be burning quickly, very quickly, like what burns in the automobile engine, the gasoline burning in the automobile engine. And that is like a bomb. Those cylinders in the engine have to be very strong, otherwise they would be shredded to smithereens. Shredded to smithereens. So that's what a bomb calorimeter is. It's a very material made out of very strong stuff, and it's not going to break down because something is going to be exploded inside it. That's why it's called a bomb, because it's going to be something is going to be exploding inside. What is going to be exploding? Ethanol is going to be exploding. And you know, ethanol 1/10 of ethanol is used as a motor fuel. It's mixed with gasoline. Ethanol mixed with gasoline, and that used as a fuel. So you know, ethanol is very combustible and it's also had a lot of energy inside it. So we want to find out what is the delta H reaction for this, or what is the heat of formation of ethanol. So that's where we are going. So here is our bomb calorimeter. We understand what a bomb calorimeter is. Now this one is what is called bomb head. And this one is called screw cap. So there's a bomb head. So we're going to put bomb head on top of it. Then we're going to put a screw cap on top of it. Then we are going to put it into over here in order to connect it with electricity, so that you don't have to put energy from outside. You don't have to introduce a spark in here, it will be done automatically like the automobile engine. You don't have to put, in order to light that gasoline, you don't need a spark, you don't need a light, you don't need a flame. It's done electronically. The bomb calorimeter is designed to explode the material inside electronically. So we are not adding more energy into it. And when this thing is going to explode, it's going to need oxygen gas. So you're going to have this bomb calorimeter will be full of oxygen gas. It will have 100% oxygen gas. The air from inside there will be banished, taken out. Oxygen tank is right here. It has 100% oxygen going in there. So that's going to be burning very fast, very quickly. That's the point. And it's going to create carbon dioxide and water, not create anything else. That's the other point. So this is close. This is how you would close it, by doing that. And this is the temperature right now. Is fluctuating because the last number is doubtful digit. So let's follow the directions. 3.8, we go over there. Page 61 or so, 3.8. Page 61, 3.8. Three 3.3, 3.6, 3.6, 3.7, and 3.8. Heat of formation of ethanol. The heat of formation is the heat of reaction for the formation of a compound from its elements. We're going to add a little bit something over here from what? From its element in their natural state at 25 degrees Celsius. That's what we're going to add to this definition of heat of formation. The heat of formation can be determined by measuring the heat of combustion for the compound and then using Hess's law. Well, I'll talk about Hess's law, but we don't need to worry about it right now. Hess's law is just what we did right now. It's just we write down that because delta H is a state function, we say my final state minus initial state is what we get the answer. We get the answer that way. And final meaning product, and initial means reactant, and final means the heat of formation of all the products. Initial means the heat of formation of all the reactants. That's what we are talking about here, okay? All right. Calorimetry experiment that measure the heat of combustion can be performed at constant volume. We are going to be performing at constant volume. We are not going to change the volume. Using a device called a bomb calorimeter. In a bomb calorimeter, a sample is burned in a constant volume chamber in the presence of oxygen at high pressure. The heat that is released warms the water surrounding the chamber. By measuring the temperature increase of the water, it is possible to calculate the quantity of heat released during the combustion reaction. So we would measure the delta T. That's what we would do, measure the delta T. In this assignment, you will first measure the heat of combustion of ethanol and then convert the heat of combustion to a heat of formation. To heat of formation, okay. So we're gonna measure the heat of combustion and then we'll convert that into heat of formation. All right, so let's do it. So you are going to do it, we are going to do it 3 times. You are going to do it 3 times. First time, you are going to do it with me and write it down. That's your trial number 1. Then you are going to do 2 trials yourself and write down the results and do the calculations. So we'll talk about that. And that's all we are doing today, unless you have something, questions. So if you get it done early, you can go. I'm starting to understand that as we go more into the semester, what they call it, the Zoom fatigue is going to increase. So I need to allow for that.
How is it going to increase?
Somebody said something?
No, I really agree. I don't know what it is with today, but me and my girlfriend are both pretty tired today.
Yeah, but I last night I had a hard time sleeping for whatever reason. So I'm a little tired too. But anyway, I am okay. But
Daylight savings is catching up with all of us.
yeah. So they are calling it Zoom fatigue. So we need to be careful about that. I don't want to have a lot of fatigue going on the students. And you are on the computer for longer than I am because you have other subjects that you are on the computer for. So I also have to remember that. So I would be available, but if you feel, you're done with this class and you need to take a break, you take a break. You have to decide that on your own. Okay. So we started, we will go for 10 more minutes and then we'll take a break. All right. This is a very simple experiment. Just see how I'm doing it, and that's how you do it. Just follow the directions. Start virtual chem lab. All right, we did that already. I showed you calorimeter cup is over there. It's already tiered, and we know the weight of the alcohol inside it. There's a cup there. Whatever that looks like a cup, it doesn't look like a cup to me, but make believe it. Okay, that's how it is in virtual experiments. This is amazing that we can do even this much on a computer. That is amazing. Okay, so now record the mass of the ethanol sample from the balance. So that's the ethanol sample, 0.7848 or 47, whatever you wrote down. You recorded that mass. All right, alcohol, ethanol. Ethanol has another name. It's also called ethyl alcohol. You don't have to remember both names. You don't have to remember the formula. Ethanol is easier to write, so we write ethanol. Okay, now the next step. We saw all this balance pan, the bomb head, the screw cap, and the bomb, and kick the calorimeter lid to close it. We already did that. So double click the following in the numerical order. Double click. First time I did it, it said double click, but I just click it single time and nothing happened. I said, what happened? Nothing happened. I said, oh, I didn't know the double click. So that's what it is. Double click the cup on the balance. So I'm double clicking the cup on the balance. All right. It's went in there. Now it's a cup. Went in there. We're going to put it in there. Now the cup on the balance pan. Click the calorimeter lid to close it. No. The bomb head. This is the bomb head. So we're gonna click that 2 times and it went in there. You see that? That bomb head is inside there now. Now the third thing is the screw cap. Number 3, the screw cap. 2 times, 1, 2. As screw cap went in there, is gone. So now this is gonna go in here. So I'm gonna click this 2 times and it's gone in there. There and there. Now we go. Now we're gonna close it. Close. Bomb is there. Close. Closed it. Okay. Click the clock on the wall, we label accelerate to accelerate the laboratory time. It takes a long time to do this. We're gonna accelerate the time so we don't have to hang around for here too long. Okay, we accelerate the clock. Click the bomb control panel and the plot window. Right, ignite, it says, you say that. Bring them in the front. We have it in the front, so that's fine. Click on the save button. Save button. So save data. Allow the graph proceed to 20 to 30 seconds. That's done. Now click ignite. Right here is ignite, and that's gonna ignite the alcohol in the bomb, and it's gonna have a little bomb that we're gonna hear. So get ready to hear the little bomb noise. Boom. Now the temperature is gonna increase, of course. All right. Allow the graph to proceed to, okay. We go up to 5 minutes. We don't have up to 5 minutes laboratory time. It will be faster than that, but now we are just waiting here. And this is the kind of data table that it looks like. Mass of sample, you wrote it down. Initial temperature, you wrote down 25.00 something.
What was
460,
the initial mass?
the mass is right there. Oh, yeah, I wrote it down, 0.7847 grams of ethanol. 0.7847 grams. Initial temperature, you can just write down 25.000. Now we're just gonna see how the highest temperature, and we're gonna write that down. And that's what we are doing. Now I can, there we go. And this is gonna show us where we're gonna be more careful. Now it's getting there, but it's not highest yet. We can see that it's still increasing. When it levels out, that's when we need to pay more attention to this changing temperature. And don't worry, this is gonna, okay, so we can see it again. It's still going up slightly, still going up.
Professor, it looks like your data table that you you gave us on Canvas is a little different than that. Do you
Yep.
want to do it
Yep.
based on Canvas?
I want it on Canvas right now. I just, because
Yeah.
you are writing it down just now, that's why this is okay. The data table on Canvas, I felt that this was not good enough data table. So I made another one. So everybody, just use this for this procedure. Do not use the rest of it. Use the stuff on Canvas. And I have also put it on file. So if you want to go on file, you can have both versions. You can have PDF versions or you can have doc, whatever you want. Now we are getting there, close to it, not quite yet. It's still going up a little bit. 27.168, 27.176, 27.186, 21.189. Da da dee 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 dim dim dim. Da 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 dum dum dum. Dee dee dim dee dee dim dee 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 dim dee dee 27.216. We are almost there now. Just pay attention now. 212, 227, 230, 0.230, 0.231. So far, 0.231, 0.231, 0.233, 0.233, 0.233, 0.234, 0.237, 0.237, 0.242, 0.242, 0.242, 0.242, 0.242, going once, going twice, gone, 0.242. All right, 27.242 degrees Celsius. Oh, 248. Haha. 27.248. Okay. 253. 27.253. 59. 260. 21.260. 61, 64, 21.264. 65. All right. 67. 67, 67, 67. 7 times 67. Oh, 270. I think that's it. 27.270 degrees Celsius. Am I solved or not solved yet?
So we go to 5 sig fig.
We are going to take 5 sig fig because that's what they are giving us. Yes, indeed. All right, we'll call it, that's the day. That's the part of the experimental part, that's it.
So then it's 27.262.
We're gonna call it 27.270. That's the last, the biggest number.
And delta T should be 2.270.
Yeah. So we get out of here now. And we are going to go into Canvas. Or we don't have to go into Canvas. I can just do it from here. All right, let's see, heat of reaction. Heat of formation. There we go. So I'm going to do this calculation with you. We're going to do it together. The whole thing, the whole calculation. And then you will do the same type of calculation for 2 trials. And you don't have to show that calculation. You just need to write the answers. So you have a format for the calculation, how to do the calculation, what calculation it is. You just have to follow that and don't even have to tell me how you did it. You just write down the answers here. That's the point. All right. Heat of formation, ethanol or ethyl alcohol, C2H5OH. Heat of formation is heat exchange when 1 mole of a compound is made from its constituent elements in their natural state at 25 degrees Celsius. For ethanol, heat of formation is the heat of reaction for this reaction. Formation is the heat of this reaction, I should say. That would be better, huh? Yeah, heat of this reaction. This reaction. How many moles of ethanol are we forming? We are forming 1 mole of ethanol. That's the magic with heat of formation. And in order to do that, we will have to take only 1/2 mole of oxygen, and that's all right. We can write fractions now. We have become big.
Hey, Professor,
Yes.
before we get in this, weren't we supposed to take a break?
Well, let's take a break right now.
Okay.
Thanks, brother.
20-minute break.
Sounds good.
Sounds
All
good.
right, 53 to 3:13.
Thanks, Professor.
All right, thanks for reminding me.
You're welcome.
Okay, bye. I'm hanging in here. If you have any question, go for it. Okay, I'm gonna turn off the recording at least. All right, let's turn that off.
The recording has stopped.
All right, all right, all right. Okay, let's get the troops back together. All right, recording, resume.
This meeting is being recorded.
Recorded, recorded, recorded. Go to the share screen. And it's 3:13, so we are on time. All right. Here we are, heat of formation. Heat of formation. What is another name for heat of formation? Zachary? I feel like singing your names. Zachary? I had to ask permission before I sing your names, you know. It's not right for me to just start singing your names. So Ligon or Ligon Zachary is not answering. So we'll leave him alone. What about Diago? Can I sing your name? Diago is not answering. You're not here yet. 20 minutes were not enough? Well, we need to know about that. If you think 20 minutes are not enough, what can I say? Okay, Makaya, are you there?
Is it enthalpy?
It is the second name for heat of reaction is enthalpy of reaction or enthalpy. Right. Heat of formation. So that's what the second name is. The same thing, or standard heat of formation, or standard enthalpy of formation, or standard enthalpy of reaction. All those things are same thing. And we don't say standard, we mean it, but we don't say it. Normally we just say heat of reaction. That's the easiest way to say it. Enthalpy of reaction is fine, enthalpy is fine. All right. Now, for ethanol, the heat of formation is the heat of this reaction. 2C, graphite. We have to write graphite because we have to take the element in its natural state at 25 degrees Celsius, which is graphite and not diamond. So we are burning graphite. Oh, we are adding graphite to 3 moles of hydrogen and 1/2 mole of oxygen to make 1 mole of ethanol. That's what we are doing. Okay. That is called the heat of reaction of this heat of this equation is called the heat of formation of ethanol. I'm going to say it again. The heat of reaction of this equation is called heat of formation of ethanol because you are forming 1 mole of ethanol from its constituent elements. So I could ask you a question like this. Write the equation for the write the equation whose delta H is going to be the same as heat of formation of ethanol. Write it down, everybody. Write the chemical equation whose, write the chemical equation whose delta H is going to be the same, whose delta H is going to be the same as the heat of formation of ethanol. Then you write this equation. That's what you will do. Delta H is same as the heat of formation of ethanol. And then you will write this equation. This is how I would phrase my question. All right, we talked about the bomb calorimeter, so we don't have to say anything more than that. Use the procedure given in the laboratory manual. So we did that. We did one trial. Everybody has first trial is gonna be the same. The other two trial you're gonna do on your own. And if you don't have that capacity, you let me know and we can do something about that. But you have to let me know. Mass of sample, you wrote it down as 0.7847 grams or 0.7, whatever you wrote it down. Let's see, we're gonna write it down. Annoyed. Okay. 0.7847 gram. Initial temperature 25.000 degrees Celsius. Final temperature was 27.270 degrees Celsius. 270 degree Celsius. Calculate delta T of water. That's going to be positive. Temperature increase 2.270 degrees Celsius or Kelvin. It's the same thing, not different. Okay, write the equation for the combustion of ethanol. Everybody is writing the equation for the combustion of ethanol. You know the formula of ethanol is right here. You are writing that reaction equation right now. Do it. Ethan, please give us the equation. You tell me and I write it down. What do you want me to write down? Ethan Shaw.
Can I write it? Can I say it, Professor?
Okay, you can do it.
Would it be 2C plus half O2?
Hold on. We are talking about combustion of ethanol. Which one is going to be the reactant?
I have it wrong. Sorry, I have to look it up.
That's all right. By doing it wrong, we learn, right? So tell me. Yeah. C2H5OH. Now it's burning. So what is it reacting with?
Oxygen tank.
And what is the formula of oxygen?
Okay.
O2. Thank you. Very good. O2. And what are the products when anything burns with carbon and hydrogen and oxygen?
Carbon dioxide and
Carbon dioxide and water. So H2O. Now we balance the equation and everybody knows in this class how to balance the equation. So I'm going to leave it to you guys to balance it. So that is the equation of combustion of ethanol. All right. Now that's point 1 is already done for you. Next. Get rid of it, clear. Calculate Q, heat released by given grams of burning alcohol. The heat capacity of the calorimeter is given to you. The heat capacity is measured by doing many experiments. That's how the heat capacity was measured. This calorimeter that we used in the virtual experiment has heat capacity. It does not have specific heat capacity. The calorimeter is not a homogeneous substance, so it only has heat capacity. And look at the units, always please, please, please make a very strong habit of looking at units all the time, even when you are not writing them down. Because units are going to tell you things. This is telling you that there is no grams involved in here. Only you have to multiply by Kelvin in order to convert to kilojoules, which is the heat, which is the energy involved. So that's all we have to do. So Q equals big C, which is called heat capacity of the calorimeter, which is this one, multiplied by delta T, which is we calculated over here is what was 2.70 degrees Celsius. And everybody remembers that 2.70 Celsius is delta T, therefore it is also 2.70 Kelvin. Same thing. So I'm going to multiply this. And as I multiply, I can see that Kelvin and Kelvin are going to cancel out. And I'm going to have kilojoules as my unit of Q, which is what I should have. That tells me that I'm doing something right. 10 point, everybody's writing this down. 10.310 kilojoules divided by Kelvin multiplied by Kelvin or degree Celsius, same thing, 2.70 K. K and K cancel out. K and K. The answer is in kilojoules, which is what we want. Q is supposed to be in kilojoules. And when we calculate this, what do we get? What do we get? What do we get? We get 27.81, and I want three significant figures because I have three sig fig over here. 27.8. 27.8. What are the units? Kilojoules, 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 kilojoules. All right. The Q produced, this is the Q, is equivalent to the grams used. That's where it came from. So how many grams did we use? We used 0.7847 grams. Grams we used. 0.78. You already have written this down. I'm writing it down to refer it to again. Grams. This is 0. This is a conversion factor. Grams equals 27.8 kilojoules. That's a conversion factor. And the starting quantity is 1 mole because heat of combustion is for 1 mole of ethanol. 1 mole of ethanol is the starting quantity. Calculate heat of combustion for trial 1 and show the calculation below. So everybody is doing this. So we are going from this is the Q. We are converting Q to heat of. This is for Q. So we are going to say 1 mole. So far, I have been good at writing this thing, so you can read it. I'm trying to be very careful so they can read it, and I don't have to write it in the other thing, which is not hard to do, but it has some little problems. Anyway, 1 mole, and the molar mass of ethanol is 44 grams per mole. I'll just take 3 sig fig grams. So I wrote it down like that. Now, Joshua, I want you to pay attention.
I'm here, Professor.
All right. See what I'm doing here. I have a reason why I am calling on you. I'm going to write down here. This grams is going to be in the numerator. Mhm. Oh. If you put the grams in the numerator here, then the kilojoules will be in the denominator. Do we want the kilojoules in the denominator or in the numerator? The answer is supposed to be kilojoules. We cannot put kilojoules in the denominator, can we? We have to put kilojoules in the numerator. We have to have something like this. We have to write this. This conversion factor must be written as 27.8 kilojoules divided by 0.7847 grams. We have to put it like that. And we have to use this here. So we say, multiply that. I have to do it like this in order to cancel the grams out. I don't want grams. I want kilojoules on the top. Everybody sees that. I don't want grams, so I have to put grams on the top here. 44 grams on the top. So I can cancel out grams. This is one way to do it. And then the 1 mole has to go in the bottom. Now, this is a little bit a different way of doing this. This is not exactly like dimensional analysis. It is dimensional analysis, but not quite what we have done so far. It is slightly different because we don't have a given starting quantity right now here. We are multiplying 2 conversion factors. You see that? This is different. Multiplying 2 conversion factors. And the answer is going to be what? It's going to be grams cancel out. Answer, the grams are going to cancel out. And what are we going to be left over with, Joshua? What units are we going to be left over with?
Kilojoules over moles?
Yes. Yep. Now, Joshua, you asked me the question the other day on Monday. Why do we write mole per mole? Is that right?
Yeah, I did ask that.
Okay, and you got it at that time too, but I'm showing you another way. Now you can see it clearly why it should be kilojoules per mole.
Yeah, that makes more sense. Thank you.
Okay, so once in a while, we are going to multiply 2 conversion factors. All right, you could have done it with 1 conversion factor by saying 44 grams is the starting quantity, and then multiply starting quantity here and multiply it with this, and you would have come up with the same answer, but 1 mole would not be in there. You would have to understand that 44 grams equals 1 more. Now, in this case, we wrote it down, 44 grams equals 1 more in here. So everybody do the calculation and tell me the answer, please. How many kilojoules per mole?
Would it be 1,558?
Sounds good to me.
Okay.
And I want to have 3 sig fig. So what would you say?
It would be 1.55 times 10 to the first
10 to the first kilojoules.
kilojoule.
1.56 will make it 6, right?
Yes.
Multiply by 10 to the 3
Yes.
kilojoules. All right.
Now, would it be kilojoules over moles?
Yes.
Okay.
Over 1 mole. Heat of combustion. We burned 1 mole of gas, 1 mole of ethanol. That's what we did. 1 mole of ethanol. So here we go. This is the answer right here that you are writing it down. Number 3. Number 4. Moving on. Can I erase this? Everybody okay with that?
I'm good.
Erase once, erase twice, erase 3 times, erased. Calculate the heat of formation of ethanol by using your calculated value of the heat of combustion. This is our calculated value of heat of combustion, and the heat of formation values given in the thermodynamics table. Write the equation of heat of combustion. Since delta H is a state function, it is calculated by subtracting the heats of formation of reactants from the heats of formation of products. Oops, it should be the other way. Oh, there is a mistake here. Okay, let's change it. Everybody change this over here, please, because it's gonna be in the canvas, it's like this. That's my mistake. Okay, let's see how we're gonna do that. We're gonna do it like this. Okay. Subtracting the heats of products. Oh, hold on. You're fine. We are fine. Oops. We are subtracting reactant from the products. That's fine. No worries. Okay, from the heats of formation of the product found in the table of thermodynamics value. So first we are going to write the equation, and that equation, writing it easier to write it with drawing than with so let's see. Let's start with this one first. Heat of combustion, delta H.
Professor, did we do number 3?
We just did number 3, I thought. Did we not?
Okay, so the 27.8 kilojoules over 0.784 grams. That's number 3.
Multiplied by 44 grams divided by 1 mole.
Then for number 2, the Q produced is equivalent to the grams used. This is a conversion factor, right? The conversion
factor, that's correct. So let's go back into that and look at that again.
Yeah, because I must have missed that.
Sure. We can look at that back again. So this is Q. And the Q has to do with how much the mass of the sample, which was 0.7847 grams. So that's a conversion factor, as you said, yes. And then we go to delta H combustion. And in order to convert from Q to delta H, Q is heat, delta H is also heat. So both of them have same units, kilojoules. So what is the difference between Q and delta H? Q is something that we get by doing an experiment. Q is something that we talk about when we are talking about grams, or we are talking about moles, grams. We are talking about grams. We took 0.7847 grams of ethanol. That heat that came out by burning that ethanol in our bomb calorimeter is Q. But delta H is not there, because delta H has to do with moles, because delta H is heat of reaction. And how do we express a reaction in chemistry? By writing down a balanced equation. So in a balanced equation, we always have moles. We don't have grams in a balanced equation. So delta H is for moles, Q is for grams. So if you have grams, convert the grams into moles, and then use that moles and to convert the heat, kilojoules, into delta H. So Q is converted into delta H in this fashion. Okay. Write the equation of delta H, and delta H as function is calculated by subtracting. So we are writing that equation now, and let me go back to it. I like to write delta like this, delta H, and superscript, and combustion is the same thing as reaction. I write combustion. comb, C-O-M-B, comb would be combustion. Comb is combustion, C-O-M. Okay, equals sum of all the heat of formations of part products, delta H F, heat of formation. Formation, this is combustion, this is formation of product, minus sum of all the heat of formation, and we mean at standard state. So we write down that superscript 0 of reactant, final minus initial. Reactants are initial, products are final in a chemical equation. React. This is the equation we use. It's a very simple equation once you understand what goes into it. Use the above equation to calculate delta HF for the ethanol for all three trials. So we know the combustion because we calculated it. We write it down. Should have given more space over here. So here we go. Write it down. What was that we calculated? 1.53, or what was it?
For the delta temperature of water?
No, the heat of reaction that we just calculated right here.
1.56 times 10 to the 3.
5.6, not 3. Okay. 5.6. 10 to the 3 kilojoules. Okay, so that's that equals heat of formation of product. What are the product? Carbon dioxide and water, right? Now this water that was produced, it was liquid water or it was a vapor water? What do you think? In the Bohm calorimeter. When that ethanol burnt in the Bohm calorimeter, water was produced. This water, what do you think it would be? Hello. Somebody please tell me, what do you think? Is it gonna be gas or is it gonna be liquid water?
It would be gas.
It would be gas because of high temperature. We are assuming that it's 25 degrees Celsius, but because we can do that because it doesn't, delta H doesn't make much of a difference when that is the case, but it is going to be gaseous water, of course. Gaseous H2O, gaseous water, kind of funny thing to say. So earlier we had, everybody wrote down this equation, I suppose. Now we're gonna need a little more space over here, so I need to do that. So let's do that calculation right here. I can write it down. This is going to be 1.56. We calculated this. Oops. What happened? 1.56 multiplied by 10 to the 3 kilojoules equals product, our two products, carbon dioxide and water. How many moles of carbon dioxide did we make? We made 1 mole of carbon dioxide by burning that ethanol. So we look up, everybody right now is going to look up the heat of formation of carbon dioxide gas. So you're gonna Google it, or you're gonna ask your Siri or your Alexa. You do that right now and write down that number right here as one of the products being carbon dioxide. So I'm gonna put a parenthesis here, I mean bracket here, and I'm ready to write down one heat of formation of 1 mole of carbon dioxide. As soon as somebody tells me that. If you know, nobody tells me that, you have a break right now. Okay, as soon as we are done with this little bit more, we'll have a break, so hurry up. Otherwise, no break for you guys today, no way. And that means no break for me, and that's not fair. I need my break. Thank you. Negative 393.5 kilojoules. And we don't have to multiply by 1 mole because it is 1 mole. We just have 1 mole of carbon dioxide. But let's do it for the goodness sake. Kilojoules per mole. This is the actual value of carbon dioxide heat of formation. And then I have 1 mole of carbon dioxide, so I'm going to multiply that with 1 mole carbon dioxide. In the equation, I have 1 mole of CO2. Okay. Plus, how many moles of water did we make?
I have 3.
3 mole of water. So we're going to say the 1 mole of H2O gas. No, let's not call it water. I'm sorry. H2O gas is 283 kilojoules negative, I believe. Is it 282 or 283? I forgot. That's 1 mole, per 1 mole. Now I'm going to multiply that with 3 mole because I have 3 moles in the equation. Oops. Mole.
That's right, actually. I don't
Pardon?
think that's right. I don't think I balanced my equation right.
I don't understand. Say it again, please.
I don't think I balanced my equation right. I don't think there's 3 moles.
Oh, you don't think there are 3 moles?
No.
Okay, well, let's do that again. All right. Thanks for telling me. C2. Oh, yeah. It's
'Cause
not
there's-
1 mole of CO2, it's 2 moles of CO2, isn't
Okay,
it?
then I did balance it right. There's 2 moles of CO2.
2 moles of CO2. That's what my problem is.
Okay.
I wrote 1 mole of CO2 here. I need 2 mole of CO2 here because that's what I have in there. I'm going to change it to 2 mole of CO2. And then we have 3 moles of O2, right? Because we have 6 hydrogen here, so it has to be 3 moles. Okay? Okay. And then 5 plus 1 is 6. 2 mole of CO2 is 4 oxygen here and 3 oxygen here. That's
That's only 5 though.
yeah. Okay, C2H5OH plus O2. So we are going to say 3 O2 over here. And that will do it, right? 7 oxygen on this side and 7 on this side. 2 CO2 plus 3 CO2, 3 H2O. Gas, H2O gas. Very important to write it down. 6 hydrogen on this side. 4 plus 3, 7 oxygen on this side. 6 plus 1, 7 oxygen on that side. 2 carbon, we have balanced. So that's good. And 283 moles multiplied by 3 moles. Now this is in the parenthesis minus the heat of formation of reactant. And what is that? Reactant is this. Ethanol is the reactant. heat of formation. So this is what? Minus delta H superscript 0, F for formation, and we write down ethanol for Eth for ethanol, okay? Eth. So we have this, we have this, we have this, we have this, we don't have this. Very easy to find this now. So everybody do the calculation and find heat of formation of ethanol. Everything is there in the equation except heat of formation of ethanol. So you can just add and subtract and multiply and divide and whatever and get the number, please. Everybody is doing it right now.
Are we subtracting the heat of formation of oxygen gas?
Well, what is the heat of formation of oxygen gas? It's an element in its normal state at 25 degrees Celsius. Do you have to make oxygen at 25 degrees Celsius? Do you have a reaction that would make oxygen? Any compound? I mean, any element? You cannot make an element, can you? You cannot form an element by a reaction. So what is the heat of formation of oxygen?
0.
0. Thank you for pointing that out. As good for us to remember that all the time. Appreciate that. Thank you. So that's 0. That's why we don't have to do anything to it. Or we should write down plus 0. Just to remind, plus 0. Thank you. Yes. So do the calculation now. Find this. There's a negative sign here. I forgot to write that. What is the heat of formation of water vapor?
Okay, I found this.
And that's what the problem is. I found my problem. I made a mistake here. The water vapor is not 283, that's water liquid. Water vapor is 282, 240, 242. Everybody, there is a problem here. This should not be 283, it should be 242. Okay, it looked like something was not right, so that is not right. After that, everything is okay. So let's change this number. Everybody listen to me and change this number. This is the kilojoules is the heat of formation of H2O gas. And so multiply by 3 mole. So that would be okay. Now it's okay. Something is not right here. I don't know what. Sorry about that. Something seems to be not right. Okay, that's the point. This is how we do it. Now, let's take a break and then we'll do there is not much else to do now. This is it. So let's take a break. It's 4 o'clock and a 20 minutes break is 4:20 and then we'll just go for 20 more minutes after that. So 4:20 we meet together again. Okay, I'm going to turn off the sharing here. Let's see.
The recording has stopped.
Big error, man. All right. 421, 420. So this is what the last thing we are doing. And share the screen. I'm not gonna record this part. I think it's okay. Now, this is what I have written down. So I wanna make sure that you have this. So let's see, everybody has this, 7847 grams. And initial temperature 25. I'm not totally sure about this. I forgot to look at it, but it probably was 25. Final temperature that, calculate delta T of water to 27 of water. Okay, everybody has this. So I don't need to do anything more. Now, write the equation for the combustion of ethanol. We wrote that down. So you have that. Calculate Q, heat released by given of grams of burning ethanol. Heat capacity is given to us here. So calculation for trial 1 only. For trial 2 and 3, calculate and then plug in the values over here in this results table. So here we are. Q equals big C. That is the heat capacity of the calorimeter, which is given to us right here. So big C is right there, multiplied by change in temperature, delta T, that's multiplied by delta T. So we get, this Q is gonna be negative, we know, because the heat was released. This is an exothermic reaction, so we write down negative here. Negative 27.837 kilojoules. And then Q produced is equivalent to the grams. This many grams we used. So negative 27.837 kilojoules equals, and I need a, there, many grams. So far so good. This many equals this many grams. This is a conversion factor. Now, come one more thing. Molar mass of ethanol is 46.068 grams. I told you wrongly that it was 44 grams. I made a mistake there. This is 46.068 grams. So that's ethanol. Now combustion, heat of combustion is going to be that. We wrote down the equation, so everybody has the equation. This is how we are gonna write it down. Heat of combustion. 46.68 grams over 1 mole, and multiply that with the conversion factor here. And when we do that, we get this number, negative 1635.7 kilojoules. So this is something that needs to be changed. Instead of 44 grams over here, it should be 46. Yeah, I was telling you something doesn't look right. That's what was the problem with it. I looked at it and I realized it. Okay. Then we have this many grams. So everybody's writing this down. This is slightly different than what we calculated. Heat of combustion of ethanol. Oh, before I forget, let me tell you, we are gonna meet at 5:45 this evening. So if somebody still have some pizzas and they need to see me and do the calculation and whatever with me, or any questions, we'll be meeting at 5:45, not at 5:30. 5:30 is a little too early for me. After getting off from here at 4:40, 4:45, sometime 4:50. So 5:45 to 6:45, that's the office hour for today. And you also have a little more time that way. Okay. Now, calculate the heat of formation of ethanol by using your calculated value of heat of combustion. This is the heat of combustion value here. So this is the last part that you are writing down again, just writing 46 instead of 44. And then this number is gonna be different. Okay. Then Write the equation of heat of combustion. This is delta H a state function. We wrote that down. So you have that. And the heat of formation of ethanol is going to be like that. So this is 1635 kilojoules. That's the heat of combustion. We put it in here. And this is the, this number comes from adding up two numbers, the heat of formations of 2 moles of carbon dioxide plus the heat of formation of 3 moles of water. So that's, this number comes from there. And then we change it so the sign becomes positive here. So I can write that down just to let you guys know over here. Let's see over here, I can write it down, I guess. So this 15, 20, 13 comes from 787 plus 726 kilojoules, of course. You can only add kilojoules to kilojoules. So that equals 15, 13 kilojoules. Becomes positive because we have to, when you do the method, the algebra, this becomes positive. It was negative earlier, remember that? So it becomes positive. That's where it's coming from. That equals the delta HF heat of formation of 2 mole CO2 plus negative sign here. Negative plus that's where this comes from. 15, that's 1533 becomes positive here, and this is what we get. Okay, the last part is data analysis.
Hey, Professor, could you scroll up just for one more second? I didn't get the last part of that. Thank you.
Mm-hmm. So the last part is you'll write down your results in here, delta H combustion, and then I'll have delta H heat of formation, one thing over here. Okay. And then you have calculate the value, data analysis, calculate the average value. We'll have 3 values here. Calculate the average value and calculate relative range, highest minus lowest. That's, you have done that before. This is the equation. True value, we have done percent error before, and this is the equation for calculating percent error. This time you are going to calculate your own personal error because I am giving you the true value right here. And this first, our 120, negative 123 and 277, that looks pretty bad to me. So we had a bad result here, real bad result. I don't know why that is the case. It's over 50% error. Okay, hopefully you won't have that kind of error for trial 2 and 3. Maybe we made some mistake while we were doing something there. Okay. Post-lab questions. That's easy for you to deal with because we have dealt with it. So that you can do. So that's what there is to it. And you have 1 week to complete this and return it to me. So any questions? All right. If you don't have any questions, you can go. I'll be here for 5-7 more minutes. You can just go. And 5:45 is the time for meeting tonight.
So the combustion in question 3 would be negative.
Yes, question 3. Right here.
And then you put that into the data table, the results table, the bottom one.
Then you will put that in the equation for the heat of combustion, which has heat of formation of ethanol in it. So what is the equation for the heat of combustion?
The sum of the heat of formation of products minus sum of heat of,
Right.
can you look at the results table, get down?
I need to write down one more result over here, heat of formation. That's what I forgot here. Or it should not be combustion, it should be formation here maybe. No, I think I'll have it. Heat of formation over here. That's what I'll do.
What is the, wait. What was it? The results for question 4 would be the heat capacity.
Heat capacity. What is heat capacity? Capacity to hold on to heat. That's what heat capacity is. Is it different than specific heat capacity?
Yes, it is.
Yeah. Specific means for a particular substance that's a homogeneous substance. So heat capacity has to do with that. But heat capacity, once we do the calculation, there is no heat capacity that we are talking about here. This is the heat capacity, Q equals C multiplied by delta T. So there is the heat capacity that's coming in right there.
And what do we put for that?
So is that clear, or did I answer your question, or what?
What would we put for trial 1 for the heat capacity?
I can't hear you very well.
What would we put trial 1 in the heat capacity?
Your voice is breaking in the middle.
What would we put for trial 1 in heat capacity?
The trial 1, that's what we did for trial 1, that's right. Heat capacity is the same heat capacity for all 3 trials because we are using the same calorimeter.
Oh, it would be 10, to 10.3.
Yeah,
1.
0.31 kilojoules per degree Celsius.
Okay.
Okay, let me write that down. So good, that should be clear to everybody. Data table, add one more data over here.
Isn't that already
It is given,
given?
but I'll write it down here anyway, just so that they may have said, well, what about heat capacity here? It's the same, 10.31 kilojoules per Kelvin, kilojoules per degree Celsius. And the same for all trials. That'll make it a little easier. Okay.
For the delta T, you got 2.27. And then in calculation 2, number 2,
Yes.
if you look at that, you use 2.7 instead of 2.27. But I did it with
Okay, there's where the problem is. This is okay, all right.
I use 2.27, but I get a positive number.
Well, Q is negative because heat came out, so that's not the thing. But so that's why that I said there is a very big the error here. That's where the error is, 2.27 instead of 2.7. Okay. All right. So let's do that again. Yeah. 10.31 multiplied by 2.27. That's going to be 23.404. 23.404. Okay. Now, then we have here 23.404 and yeah. Okay, and that changes the value here.
And I got 1,374.
Oh boy, it's getting worse.
I think so.
Yeah.
If you
1,000 is even 74.
be 46.07 and negative 23.
Things are getting really worse now, huh? I don't know. I don't know what happened. I'll have to look at it and then let you guys know about this.
All right. I think in the last lab, we were also super far off the true value.
Last lab looked okay to me, but okay. Thanks for letting me know. All right. I'll look into this and let you guys know what's going on.
I'll probably be coming by later.
Pardon me?
I'll be coming for office hours. most
Yeah, I'll be here 5:45.
likely. Bye.
Okay, bye.